Sinusoids and complex exponential waveforms of time. The general form of a sinusoidal signal is A cosine omega t plus theta. This type of signal is completely specified by its three parameters, A, omega, and theta. A is the amplitude, omega is frequency in radians per second, and theta is the phase shift of the sinusoid. A quick review. Omega equals 2 pi f, where f is the frequency of the sinusoid in hertz, or cycles per second. So the sinusoid can be specified either as a function of f in cycles per second, or in terms of omega, in radians per second. What is the meaning of omega's units, radians per second, anyway? Well, imagine a wheel having radius r rolling on the ground. What is d? The distance it had rolled after one complete revolution. The answer is d is equal to the circumference of the wheel equals 2 pi times the wheel's radius. We can describe the wheel's rotational speed in terms of how far it rolls in 1 second. Of course, this distance depends on the size of the wheel. A better way is to use a normalized distance. One way to normalize distance is to divide it by the wheel's circumference, which equals the number of revolutions of the wheel per second, that is frequency f. Or we can normalize distance by dividing it by r, the wheel's radius, giving the number of radius lengths rolled by the wheel in each second, in units called radians per second, which we call radian frequency omega. So there really is not much difference between omega and f when measuring frequency, only the scale factor 2 pi. In this course, we will write mathematical expressions in terms of radian frequency omega. Theta is also specified in radians. On the other hand, practicing engineers use frequency f in hertz or cycles per second and phase shift theta in degrees almost exclusively. Now that we've looked at the sinusoid, our next signal of interest is the complex exponential of time. By expanding this function using Euler's formula, we see that its real part is a cosine and its imaginary part is a sine. Both of these components have frequency omega, so e to the j omega t is set to have frequency omega. Note that the magnitude of e to the j omega t is 1, and its phase angle is omega t radians. Therefore, treating omega as a constant, e to the j omega t represents a vector of length 1 that spins in a counterclockwise direction at a fixed rate as time increases. The number of cycles per second this spinning vector makes is f equal omega over 2 pi. Note that e to the j omega t appears simpler to describe than its real and imaginary sinusoidal components. The complex exponential function will form the basis for linear system analysis and Fourier transforms that we will study later.